Good morning, everybody. Welcome to Argonne National Laboratory's Science at Work webinar series. Today, we're going to hear about blocking threats to supplies of rare earth minerals. My name is John Harvey, and I'm a business development executive in Argonne Science and Technology Partnerships and Outreach Organization. Just a few logistical notes before we get started. For a better experience, we recommend turning off your VPNs. If you're having any trouble at all, we recommend logging out, logging back in. Your video and audio were automatically muted when you join the webinar. Therefore, we encourage you to ask questions via the public chat function. Because of this is so short, we will probably not answer those questions during the webinar, but we'll get to them via email after the webinar has ended. Finally, please note that today's webinar is being recorded and will be made available to everyone for viewing at a later date. Now I'd like to take the pleasure to introduce our speaker, Allison Bennett Irion. Allison is a principal systems engineer and group leader for Argonne's nuclear radiological proliferation analysis and modeling team. She is the chair of Argonne's Advanced Supply Chain Analytics Initiative and an Atlantic Council Veterans in Advanced Energy Fellow. Allison, we look forward to your remarks.
John, thanks for the kind introduction, and thank you to everyone who has joined us today. Let's jump right in on what makes the material critical or rare in the first place. Critical materials are defined as being important to the US economy and national security. This creates both a risk and an opportunity. They are subject to supply risk due to import reliance, concentration of production in non-allied countries, and they possess unique characteristics that make them difficult to be substituted. As an example, cobalt is used in the precursors and cathodes of rechargeable batteries. Around 70% of cobalt is mined in the Democratic Republic of Congo, with the vast majority going next to China, where they dominate refining, particularly for chemicals suitable for battery applications, with China accounting for 80% of the global output of cobalt sulfates and oxides. The list of what is critical or is not critical is dynamic. Material criticality is intertwined with technology advances, with materials falling into or out of criticality as their application in high demand technology increases or diminishes. So what are these critical materials used for? Critical materials are used in a wide range of domains, from energy to defense to transportation. And some of the attractive characteristics include luminescent properties, where critical materials are used for LED displays and cell phone cameras. Magnetic properties allow neodymium iron boron or neomagnets to be the strongest permanent magnet available, and they're particularly key when space and weight are limiting factors. Neomagnets are used in hard drives, a number of automotive applications, and generators for wind turbines. China controlled 90% of their supply, and we saw prices double during parts of the pandemic. So what's Argonne doing in this space? Critical material research can reduce risks with innovation focused on technology, materials, and supply chains of the future. Securing the supply of critical materials requires a cohesive approach to diversify supply, reduce demand, and ensure energy materials sustainability and social justice. Technology investment decisions should be grounded in an understanding of risk dependencies, material availability, and supply chain dynamics. Integrating tools that can assess these interactions into early stages of the R&D process can help guide the development of environmentally and economically sound solutions. Today, I'd like to share about one of our tools here at Argonne, our agent-based global material security, global critical materials, or GCMAT model. It was initially developed to help DOE to better understand the implications of supply disruptions of rare earth materials for electric vehicles and wind turbines, with the goal of investigating supply chain dynamics from mining to final production. GCMAT has also contributed to the Department of Defense Logistics Agency's National Strategic Stockpiling Decisions. GCMAT uses Repass Symphony, an agent-based modeling platform developed here at Argonne, and our high-performance computing resources for model calibration and uncertainty analysis. For those of you who may be less familiar with agent-based modeling, we use this technique to capture interactions, decisions, and dynamics across the entire supply chain, enabling the evaluations of strategies, consequences, and risk of supply disruption on both the supply and the demand side of the market. Agents represent each supply chain stage, from individual mines to refiners that process the ores, to magnet manufacturers, to final products. such as electric vehicles or wind turbine producers. Each agent adapts, updating their behavior and production forecasts in response to market prices. This leads to decisions such as when to begin or end construction of a mine, on setting production schedules, and pricing for intermediate uses. This represents, how a real mine would make these decisions. There's also diversity of decisions among suppliers and buyers in the way they are affected by different market conditions and information. Calibrating to historic data, our parameters match past market shocks, which help us improve our ability to forecast future disruptions. Because GCMAT can model causal dynamics and provide fine-grained representation of agents and their decisions, it provides some explanations for turning points under market conditions that are not otherwise available from other modeling approaches. Currently, through Department of Energy directed R&D funds, GCMAT is being extended to battery materials, including lithium, cobalt, and nickel, and a recycling agent is being added to evaluate future market scenarios. We're also creating a more generalizable version of the model that allows for more quick pivots from one material supply chain to another so that GCMAT can be more agile and be part of a broader supply chain toolkit. Next, I wanted to share some key findings from some of our recent research. In our publication earlier this year in Resources, Conservation, and Recycling, under Argonne's lead author, Matt Riddle, and co-authored with Department of Defense DLA and USGS, we explored the impacts of plausible supply disruption scenarios, such as a one-year export stoppage from China or a shutdown of a rare earth mine. We modeled Mount Weld in Australia, and a separation facility. Our example was Lynas in Malaysia. We looked at this impact on 10 rare earth elements and associated compounds to study how the consequences of supply disruption differ by disruption type and why that is. We also wanted to look at how supply disruption affects rare earth element trade. We found that the impact on demands, pricing, production, and capacity could extend years beyond the short-term event. Price increases are not really surprising. This is similar to the rare earth market response to Chinese export quota reduction and export embargo to Japan in 2010. But what was unique was how the specific type of disruption had a great impact on pricing. Disrupting Chinese exports for rare earth oxides only versus rare earth oxides and rare earth metals resulted in different results to the neomagnet supply chain, with non-Chinese magnet producers impacted more with both oxide and metal export stoppage. Non-Chinese magnet production was only minimally affected when only oxide exports stopped, as they could still obtain metal from China. When both oxide and metal exports stopped, non-Chinese magnet producers dropped relative to the baseline levels. And when Chinese export resumed, the non-Chinese magnet producers recovered, but still remained below that baseline level. The results highlight which rare earths are most vulnerable to disruption, with the largest price increases occurring with dysprosium oxide that were even higher than what was experienced in the 2010 to 2011 rare earth element market disturbance. It's important to note that China supplies more than 90% of dysprosium oxide and metal, and a large share of dysprosium oxide is produced illegally. This accounted for 53% of the market production in 2021. Of the scenarios we studied, a reduction in illegal supply from China would have the most significant impact on EV production. This would impact dysprosium and didymium prices, which could all have a noticeable impact on vehicle prices overall. Next, just want to talk about what are the type of questions that GCMAT can answer. GCMAT can be used to examine the impacts of complex decision-making and external forces. Some of the current questions we address are, what market conditions are required to start up a mine? What happens to the market when a mine closes? What is the impact of substitution to a specific material market? As we examine R&D pathways to increase supply chain resiliency, GCMAT can be used to answer, which R&D pathways are viable for robust domestic energy storage strategy. This can assess recycling, technology substitution, and increased domestic or global supply. It can also be used to evaluate risk mitigation strategies by comparing the effectiveness of building domestic supply chains at different stages or with contracts made with allied countries. And it can also look at what extent increased domestic extraction, processing, and manufacturing could improve supply chain resiliency, and explore how might a rapid increase in EV demand impact their domestic and global supply chain. As we look at approaches to successfully build out a domestic supply chain, our GCMAT battery version could be used to answer questions such as testing if decarbonization and supply chain goals could be met through proposed action plans, and answer questions such as how might domestic battery material sources or recycling capacity affect the EV market. and also what impact would be on a cobalt and nickel markets if high nickel, low cobalt batteries are adopted. GCMAT can also be used to look at US competitiveness, helping to optimize development, deployment, and schedules and locations for lithium ion battery recycling in the US. Just wanted to say thank you for taking the time to learn about some of our critical material work here at Argonne. We are excited to apply GCMAT to battery materials and other material markets in the future, and welcome any further questions or engagement.
Great, thank you, Allison. That was a really, really great talk. Looks like we have time for a couple questions. So first, what supply disruptions would have the largest effect on the production of electric vehicles?
Thanks, John. So while we didn't have this particular study in our paper, we would think that the scenario with the greatest impact to EV production would be supply disruption events that could cause neomagnets to become unavailable. That would be the one that I think would have the greatest impact.
Great, and another one sort of in a similar vein, what are the sweet spots for US domestic supply as we transition to EV?
Sure. So, I mean, as we look at, supply chain holistically at an end-to-end approach, we do need to target value-added stages. So these are best located, one step upstream or downstream of a domestic or allied supply, chain node, to ensure that we have some US connecting capabilities and don't have, single source, sole source issues. Also, selecting or requiring specific supply chain steps to occur in the US may make it less economically viable for adjacent steps to happen outside of the US, which can be helpful. And I would also add that the US is at the forefront of innovation in this area. And as we innovate, we need to be mindful of creating, these geopolitically sensitive single and sole source dependencies. And while we're applying our innovation to build out domestic supply chains in step with these applications.
Great, thank you. And one final question, kind of on a different vein. Can your work examine the supply chains of other non-critical materials?
Yes. So, right now through the LDRD program that we're doing, we're creating this more generalizable version of the model, and so we want to be able to have those quick pivots. We've done studies before on helium and other markets, which were a little bit trickier to do because our framework wasn't built for those quick transitions. So, in this year, we're going to have that capability to be able to quickly move to other material markets.
Great, wonderful. Thank you again, Allison. Really appreciate it.
Thank you, John.
And thank you all again for attending the event today. I want to remind everyone that we will send written answers to the questions you sent via chat today, along with a recording of Allison's talk. If you have any questions or would like to learn more about how to work with Argonne, please reach out to partners@anl.gov. That concludes our webinar today. Have a great day.